Yes, we do live in the information age, and this information is being stored in tighter and tighter spaces and being transmitted at higher and higher rates with more and more interference. So error correcting or detecting codes are becoming more and more important today. And as I briefly discussed in digital logic class, adding redundancy via parity bits can allow us to perform error correction on data. For example, consider sending one of 4 different code words, that is 2 bits of data. But instead of sending the 00 to 11 code words, let's send 6 zeros, or 6 ones, or 3 zeros and 3 ones, or 3 ones and 3 zeros. What does this allow us to do? Well, let's say that we have a transmitter and a receiver, and that the transmitter desires to send the all zeros code word. But it is being sent across a noisy channel. That is a channel whose noise can create errors in the data. And so as the code word is being sent, noise indeed rears its ugly head, and the first bit of the code word gets changed from a 0 to a 1, which is what the receiver receives. So what does the receiver do when he obtains this word, which is not a valid code word? Certainly he knows it's not valid, because he knows the 4 possibilities to be sent. And so he could ask the transmitter to send it again. But maybe the transmitter can't. Is there anything the receiver can do to get this message? To understand just how error correction works, consider these 4 code words being plotted in a 6-dimensional space, which of course is pretty hard to draw on a 2-dimensional slide. And notice here that I've drawn these code words such that they are all at least a distance 3 away from each other. And by distance, I mean the number of bits that must be changed in order to make one code word another. For example, 000111 is 3 away from the all zeros code word, and the all zeros code word is 3 away from 111000, and 000111 is 6 away from 111000. Of course, it is too difficult for me to place the all ones code word on this page, because it is 6 away from the all zeros, but only 3 away from the other 2. So I'll just place it down here. This separation of at least 3 bits is crucial in our construction of an error correcting code. So, where would the received word of 100, 000 from our earlier transmission example be plotted on this graph? Well, it could go here, which is indeed a bit distance of 1 from 000, and 2 from 111000, and 4 from 000111. And it would be a distance 5 from the all ones case if we could show that on the graph. This bit distance from one code word to another is called the Hamming distance between code words, which was named for mathematician and coding theorist Richard Hamming. And the Hamming distance of a code is the minimum distance from any one code word to any other distinct code word. So what is the minimum distance of this code? Well, it is 3, since every code word is at least 3 bits from any other. So for review, what are the Hamming distances of the following received words from each code word? First, the 000001 word. It is 1 away from the all zeros case, and 2 away from the 000111, and 4 away from 111000. So how about 000101? Well, it is 1 away from 000111, and 2 away from the all zeros case, and 5 away from the 111000. Well, what about 100001? It is 2 away from the all zeros case, and 3 away from the other 2, making it extremely hard to show on this 2D graph. But But the most important question is, how do we decode these erroneous received words? Well, for the 000101 case, we would assume that a 000111 was sent, because it is closer to that code word than any other. Notice that if any code word is at least 3 bits from any other, that is, the Hamming distance of the code is 3, then if we were to move a distance 1 away from the code word, that is, change a single bit, we will still be at least 2 bits away from any other code word. And this is the basis for error correction codes.